Can everyone see?
Yes.
Brilliant, fantastic. Well, so thank you very much, everyone, for joining this webinar. I'm Patrick. I work as a solution director at Ori, and I've scheduled a session today to discuss AI productivity and GPU optimization. There are a number of topics that we will cover today. First of all, we're going to go quickly through the impact of GPU productivity. What does it mean to be efficient? What does it mean to be inefficient? And what are the implications that these issues can have? And then we will be looking a little bit more into the details of what it means to actually be productive with a GPU. So the lens through which we're going to look at these aspects is really through a computer scientist view and explore how this applies to typical AI workloads that people may use for their businesses or for their research. And last but not least, we're going to look into how we can help at Ori in order to maximize your productivity and reach your goals. So without further ado, let's get started. Um, Looking at various studies, there are a lot of people who like numbers and who like to look at what are the different expenditures associated with AI factories. And one of these institutions called Hyperion, they are a market analysis company, and they've been looking at the market for a long time. And based on their knowledge, based on the data that they capture regarding supercomputers used for AI, they provide market reports. And recently in June, they shared an update where they went into the details of where the costs are coming from when running an AI supercomputer. And it shouldn't be a surprise that servers, and in particular GPUs, represent the bulk of the spending. And typically, if a end user is purchasing access to GPUs for AI training or AI workload, about half of their expenditures is going to be just on the cost of running GPUs and energy associated with that. Now, just doing a few basic math, the implication of using GPUs inefficiently can be fairly catastrophic. So if we're looking at the financial impact of using, say, 1,000 GPUs inefficiently, 30% or 50% or 80% loss of efficiency, we are literally looking at millions of dollars of investments that are lost. And although it is quite common for people to run their GPUs at 70% or 80% efficiency, because that's life, there are many pitfalls that can happen and that people may or may not be aware of that might impact their business and their finances very heavily. And I've witnessed this myself firsthand not so long ago. And I've seen a case of an AI startup that wanted to train multimodal LLM models on a whole bunch of GPUs, was about 1,000 GPUs. And they were working in partnership with an AI service provider, which was not Ori, was not us. But they went ahead with the collaboration, and they were expected to get access to about 1,000 GPUs over the course of 3 to 4 months, with the aim of training the model at the end of that period. So they started by doing a few benchmarks, a few tests, verifying that the environment was suitable, that everything was working. And obviously, these benchmarks were done at small scale, as anyone would do when you're just doing a trial. And everything seemed to be fine. However, when the customer signed for the project and decided to go to production, they're starting to run at larger scale on the full 1,024 GPUs. And all of a sudden, the performance of their training completely collapsed. There were issues with GPU to GPU communication on the system. Writing data on storage on fast drives took a long time. So we were talking about minutes rather than seconds in order to do checkpoints, which is something that is very, very common when you're training large models. And as a result, the GPU efficiency during that training completely collapsed. And instead of being at 80 or 90% efficiency, the model was really using just about 30% of the computing capacity that was available on the system. So the customer went ahead, nevertheless, trained the model the best they could over the course of the 3 months, which was the reservation that they had access to. But at the end, when the reservation was no longer available to them and had to be passed on to another customer, the end result for this particular startup is that the training of their model was just not done. And in order to complete that project, they had to go back, find another service provider. They had to go back to procurement, sign another contract, and rerun essentially most of the training job that they just couldn't run before. And as a result, the cost for this company was not just the cost of the GPUs that were not running efficiently. It's literally the cost for the business of launching a product with 4 months delay. So obviously this customer was not very happy. And as you can imagine, the service provider that offered this infrastructure did not have a jolly time either. They lost their customers, obviously, they've got a bad reference. They realized fairly quickly that the investment that they had made on their infrastructure was not suitable, and ultimately they declared bankruptcy in the early months of 2024. So this is just a small example to show that GPU optimization is not just something that is nice to have or that will help to save a few pennies on the investment that you're making. It has a real, genuine impact on businesses, on your ability to launch your product to market quickly, on your ability to generate revenue as a company. So where does this performance come from? I propose in this webinar to look at GPU optimization and efficiency through the lens of supercomputers as data processing facilities. So everything starts with the data, and the data at the beginning of the journey sits somewhere with the users. And the first step is to bring the data close to the GPUs, typically an object store or some fast storage that will be local to the GPUs, because once the data is local to the supercomputer, it needs to be loaded onto the GPU servers, onto the memory, and then onto the GPUs, at which point that data is going to be processed by the GPUs. And when that happens, depending on the model that you may be using, whether you're doing training or inference, you may need some ephemeral storage, which can be local drives. It can also be some fast storage, such as a Weka or a VAST or a DDN, on which the servers are going to be doing a lot of writes, lots of reads, in order to perform the computation. At the end of which, the servers are going to return the results of the compute, and that data can then be sent back and used by the user for whatever purpose that they might want to do. So this model of data processing shows very easily that there are multiple ingredients or leverages that have an impact on the GPU performance. It's all about getting the data close to the facility, close to the compute nodes within the GPUs, and depending on what the workload is doing, there may also be the need to move data onto storage, etc. Which means that in order to extract the most performance out of the GPUs, it's not just about having the most performant GPUs. It is something that matters, but there is a lot of different elements that go around the GPUs that are truly important, like the connectivity of the data center, the throughput, the latency, of the storage fabric and the storage components that you have. The amount of memory that you have in the nodes will dictate whether you are able to feed the GPUs directly, or whether you need to tap into an object store or some other kind of storage environment in order to get access to your data. So all of these components play a role, and they all interact together. So one of the questions that was raised when I presented this slide to some of my colleagues was, but what are you talking about here? Are you talking about training? Are you talking about inference? I'm actually talking about all of it, because I'm looking again at a supercomputer as a data processing facility. The type of workload does not really matter. The fundamentals of feeding data to the GPUs and extracting that data back onto a platform that can be used remains identical regardless of the workload that is running. It can be training, it can be inference, it can be anything else. It is exactly the same thing. Now, obviously, depending on the workload that people are going to be using, the different ingredients that we have seen will have different expectations on them. The type of workload is going to dictate the intensity that will be expected from the supercomputer in order to process the data. Typically, if we're doing an NLP inference, in order to get decent performance, we only need a fraction of a GPU with a very small memory footprint, and there's not going to be any kind of communication from GPU to GPU because all the calculation is done locally. When we're looking at a much bigger model, large language model, and we're looking at doing trainings, all of a sudden the requirements are very different, and we're talking about thousands of GPUs that are required. The data pressure on the memory, on the communication, on the storage becomes extreme. And obviously there is a whole bunch of different scenarios in the middle with different types of requirements, which leads me to how we approach GPU performance at Ori. And we have developed a holistic methodology that allows us to look at whichever workload you may be using and making sure that at the end of the day, the workloads are going to run efficiently as fast as they can, making the most of the supercomputer and the system that is available. So if we go through that roadmap step by step, I think that in order to understand how to get the most out of the system, the first step is really to understand what the use case is going to be. The requirements on the system and on how to optimize GPUs are not going to be the same if we are going to do some training, or if we're going to do some inference, or even conversely, if we are doing some sort of complex workflows that will mix traditional simulations like digital twins combined with machine learning. This is another complete different realm of optimization and how to make the most of a system. But understanding what are the workloads that are going to be running on the system gives us insight into what are the kind of profiles we need to expect, and gives us some hints about the solution that would be required in order to run these use cases. In some cases, customers just have one or two systems or one or two workloads that they want to run. There are a host of people who have a variety of workloads, and then it becomes an exercise of figuring out which are the workloads that are going to be the most used. Do we need a system that is hybrid, maybe CPU only computing, or with GPUs, etc.? So these kind of questions also come into play when trying to define what's the architecture that is going to be best for the application. Now, once we've gone through this initial exercise of understanding really quickly what it is that we're trying to achieve, there are more technical steps that we're not going to go into the details today, but we're going to lay them out, and we can discuss them, and we'll arrange some follow-up sessions on them. But in the context of inference, one key element to look at is really model compression. Inference is often a type of workload that will rely on sparse matrices, lots of zeros, lots of things that are not really necessary. But yet the whole model, the whole data sets can take a lot of space. And in order to be more efficient, it is sometimes possible to prune or to do some pruning or to do some quantization of the models in order to reduce the size and therefore to reduce the footprint that the application is going to have on the GPUs. So this is one step in the context of inference that can be key and that can really help avoid wasting GPU hours unnecessarily. Another important aspect is really around parallelism, and we're going to dive a little bit deeper on that particular topic in the subsequent slide. But there are multiple forms of parallelism when it comes to running AI workloads. We've got data parallelism, pipeline parallelism, tensor parallelism, and obviously any kind of mixture of these. And these techniques of taking an AI model, taking the data set, and deciding how we're going to split the work across multiple GPUs, potentially multiple servers, is exceedingly important and has a very, very big impact on the efficiency of the GPUs. If this is not done properly, it is very easy to end up with GPUs that have most of the effort on them and some other GPUs somewhere else in the supercomputer that are completely idle for whatever reason, either because the data doesn't reach them or because there are some dependencies in the data, etc. So parallelism in itself is a very important topic that can really make or break the performance of a system. Once we've figured out that we've compressed the models, we've defined a level of parallelism that will be adequate, it's all about feeding the GPUs and making sure that the data management is successful, making sure that the data is local to the supercomputer, local to the GPUs, making sure that the data can flow seamlessly from whatever storage to the GPUs is very important. And designing the right storage solution is absolutely critical in order to do that successfully. And once these elements are in place, the next level up in terms of GPU optimization is really to look at how to optimize what is happening within the GPUs themselves. And this is where we start talking about do we need to, can we use a PyTorch or a TensorFlow, or should we write a code and use CUDA? We will be starting here, looking here at making use of optimized libraries or using mixed precision if relevant in order to scale things up. And this is really looking at the GPU from the standpoint of the data is there. It is on the GPU memory, but we just want the GPU to use all the tricks in the books in order to make the computation as quick as possible. And this can be very, very low level optimization. It can be as complicated as we want. And it is in the optimization and GPU performance quest process, this is typically the last step. And once all of these steps are done, I think that most of the performance problems, most of the obvious pitfalls are typically resolved, and you're getting close to the best performance you can possibly get on GPU productivity. And these steps can take a significant amount of time. So again, it's a question of balance about how much time are we going to spend trying to optimize our workload for the GPUs versus how much time we have in order to do whatever it is that we are trying to achieve with our supercomputer. But before I move on, I just would like to invite all of you, right, either in the comments, the questions, or later after the end of the webinar, is to tell us which of the GPU optimization topic in particular you would like to dive into. We're probably not going to do that today in the spirit of time, but really I think that GPU optimization is a very broad topic. We can spend hours and hours talking on it. And this particular session is really a high-level overview of all the key things that are important for AI and GPU optimization. But I believe that there is room for us to have follow-up sessions that are perhaps more technical, going more into the details of how to extract performance out of GPUs. And in particular, if any of you in attendance have an interesting performance challenge, a workload that you think doesn't run all that well, and you would like us to, dig our teeth into it and try to make it better. And if you want to share this with me and Ori and the community, maybe we could arrange some work and use this as a case study for a future technical webinar. So by all means, please let us know, and we'll be quite happy to work on this with you. Right, so let's have a look a little bit about parallelism, and in particular parallelism when it comes to training. So I mentioned that this was one of the key steps in the performance analysis roadmap. And yeah, because it's something that is fairly easy to tweak and change and can yield very spectacular results sometimes. So very briefly, I'm going to explain the key methods of parallelizing a workload on AI. So there's first of all data parallelism, which in other words is also so-called Monte Carlo. It's when there is very little synchronization between the data. We're just taking lots and lots of different data points, and we are parallelizing the entire pipeline on a specific GPU. So this is one method of parallelizing things, which is fairly easy. I think that it becomes complicated when the data sets are big and do no longer fit in GPUs. Tensor parallelism is a different method where we are going to split the tensors themselves across the GPUs. And again, this is a method that can be very powerful. However, and it typically requires less memory within the GPUs, depending on how things are split. However, the impact here is that it's going to introduce a lot of communication, a lot of dependencies between GPUs. And typically, if the model is complex and complicated, it can result into very, very heavy traffic on the GPU to GPU fabric. And the last example is really about the pipeline parallelism, where we are separating the layers and distributing the layers across the different GPUs. And again, this is something that can be extremely powerful. But again, this creates dependencies between the different, obviously there are dependencies between the different layers, which translate into dependencies between the different GPUs. But more importantly, even though this method can be extremely powerful, the danger here is really about making sure that the layers represent a similar amount of workload, right? So this is the key thing, is we want to make sure that all the GPUs have a similar amount of workload, and that the communication is not going to hinder the ability to compute on data. And in practice, if we run some benchmarks to compare these different levels of parallelisms, typically on a transformer-based language model, what we can see is that depending on the scale, depending on the model that we pick, the GPU utilization and therefore the GPU performance can drop, right? And we can lose 20, 30, 40% of GPU utilization by using a methodology that doesn't work all that well. So running, if people have the time, running benchmarks, trying to understand which level of parallelism is best, what kind of mixture of data parallelism and pipeline parallelism together, for instance, would be the best suitable, can often translate into dramatic speed up in terms of GPU utilization and performance. But with all that said, it's not all about maximizing utilization or maximizing the optimization of the GPU, because we can look at the problem from two different angles, and it all boils down to what are the objectives that you're trying to reach with your solution. There are some companies and institutions that are going to be prioritizing runtime because they need the models to run as fast as possible. They're going to be prioritizing the number of tokens per second. And in this particular case, they will seek to increase the number of GPUs, even if they acknowledge that the GPU utilization is not going to be the best, and it's not going to be super fantastic, because their priority is really to get things done quickly. On the other hand of the spectrum, especially when we're talking to academia and others who are doing more research, they're not necessarily worried about being as fast as possible. They're more worried about maximizing the total cost of ownership and making sure that their system is going to be as productive as possible. And they are happy to give up on raw performance in order to stick to the sweet spot of where the GPUs are going to be the most efficiently used. So these are the kind of trade-offs to take into account and to think about when trying to reach what the sweet spot means to you. And this is true if you're running in a public cloud and deciding how many GPUs you're going to use for your workload, or if you're developing or installing a private cloud environment for your company. So these are all trade-offs to bear in mind. And typically, these are the kind of things that we can help with. I mean, as you've joined this webinar, you probably know who we are, and I'm not going to talk too much about that. But basically, we're specialists in providing public and private cloud offering. And one of our strengths is really our ability to accompany our users and work with them in order to find that sweet spot for them, for their particular use case, for their particular model. And we've got the resources and the talents in-house to take you through this GPU optimization journey, looking at your workload, looking at what you're trying to achieve, looking at different techniques that can be used in order to make sure that whatever infrastructure you decide to acquire or use is going to yield the best results. Right, so this is taking us towards the end of this brief webinar. So some of the takeaways that we've seen is that GPU productivity can matter. For people who are casually running workloads on one or two GPUs and then not too bothered, yes, okay. Optimizing workloads for GPU efficiency is not really that important. But as soon as you're talking about serious workloads running on hundreds, thousands of GPUs, the cost of GPU inefficiency is not just the computing cost, it is also the impact to the business, the opportunity cost, the impact it has on launching your products and things like that. GPU performance is a balancing act. So this is the second key takeaway. It's not just about looking at the compute kernel that is running on the GPUs, making sure that all the tensor cores are being used, etc. It is one important aspect, but it's not the only one. The biggest and the most important aspect is making sure that these GPUs are fed, that the data is local to them, can reach the cores, and can be processed as quickly as possible. And that comes through having the right architecture, the right infrastructure, but also making sure that the data is presented to the GPUs in the best possible way so that the GPUs can actually digest them as well as possible. And then making use of all the optimized software that NVIDIA or AMD or other GPU providers can offer is also very important, as this is what will will squeeze out the extra bit of performance that the GPUs can provide. And as mentioned, I mean, we are here to help. And even if it's just an interesting exercise for you that you've got a performance problem, you would like us to help you look into it, please do reach out, and we'll be happy to have a look and see how we can support you and make sure that you make the most of your GPUs for your AI workload. So thank you very much. If there is any question, I would be very happy to try and answer. No question? No. So there's a question someone's asking about the private cloud, and is asking at what scale can we provide private cloud offering. So at the moment, we're working on a number of deployments. I think that the private clouds, or the smallest private clouds that we're working on at the moment, are at about 1,000 GPUs, but we're also working on much bigger environments. And if this is something that you'd like to explore, I mean, we can help. For our public clouds, reservations can go from as little as 1 or 2 GPUs to a lot more, if these are the kind of things that you're looking for. Is there any other question? Nope. Well, if not, then I think that we can probably wrap up. So thank you very much, everyone, for joining me today. And again, if you would like to reach me, send me an email, give us a shout, and we'll be happy to take it from there. So thank you, everyone, and talk to you very soon.